Beam me up, Scotty. The reality behind quantum teleportation. When we hear the phrase, beam me up, Scotty, most of us immediately think of science fiction. The fantastical teleportation technology used in Star Trek to transport people instantaneously across vast distances. While such a device remains far beyond the realm of current human capability, a fascinating form of teleportation already exists, not in the realm of matter, but in the mysterious world of quantum physics. This real-life counterpart is known as quantum teleportation, and although it doesn't involve the physical transfer of people or objects, it represents a groundbreaking way to move information from one place to another with astonishing speed and precision. What is quantum teleportation? Quantum teleportation refers to the transfer of quantum information, specifically the state of a quantum particle, such as the spin of an electron or the polarization of a photon, from one location to another. It is essential to understand that this does not involve the transportation of matter itself, but rather the exact duplication of a particle's quantum state onto another particle, often located at a significant distance. At its core, quantum teleportation relies on a phenomenon known as quantum entanglement, a state in which two or more particles become so deeply linked that the state of one immediately affects the state of the other, regardless of the distance separating them. This connection occurs instantly, a concept that challenged even the greatest minds of physics. Einstein versus Bohr, a philosophical duel in physics. The seeds of quantum teleportation were sown long ago, during the intense debates between two of the greatest physicists of the 20th century, Albert Einstein and Niels Bohr. Despite their friendship, the two had fundamentally different interpretations of quantum mechanics. Bohr advocated for the strange and counterintuitive implications of quantum theory, particularly the idea that entangled particles share a single, unified state even when separated by vast distances. According to this view, measuring one particle would instantaneously determine the state of the other. Einstein, on the other hand, found this idea deeply troubling. He derisively referred to it as spooky action at a distance, and insisted that no information or influence could travel faster than the speed of light, as dictated by his own theory of relativity. He believed that each particle must carry its own distinct, predetermined state, and that any observed connection between them must involve a signal traveling at or below light speed. Experiments confirm the spooky truth. Although Einstein's skepticism was reasonable for his time, decades of experiments have since confirmed Bohr's interpretation. Starting in the late 20th century and continuing into the 21st, physicists have shown again and again that entangled particles behave in ways that defy classical physics, suggesting the presence of non-local interactions, where a change in one particle is reflected in its entangled partner without any physical transmission of a signal. These results were not easy to obtain. The experiments required incredible precision, advanced equipment, and highly controlled environments. But the conclusions were undeniable. Quantum mechanics allows for connections that transcend traditional ideas of space and time. The Chinese quantum leap, entanglement in orbit. One of the most astonishing demonstrations of quantum entanglement took place in 2017, when Chinese scientists launched a satellite named Mischius. The goal was to test whether quantum entanglement could be preserved over vast distances in space, far greater than had ever been attempted on Earth. The results were astounding. Mischius successfully generated and transmitted entangled photon pairs to two ground stations over 1,200 kilometers apart. Because space is largely empty, the photons traveled through a vacuum, free from many of the disturbances that degrade quantum signals on Earth. The entangled states remained intact during their journey, demonstrating that quantum entanglement can persist over planetary distances. This experiment marked the beginning of what some call the quantum internet, a new communication network based on quantum principles, offering unprecedented security and speed. A simpler approach, one photon, two atoms. While large-scale experiments in space capture the imagination, equally fascinating progress has occurred in controlled laboratory settings. Scientists at the Max Planck Institute for Quantum Optics achieved quantum teleportation using just a single photon and two individual atoms. In their experiment, one atom, the sender, held a qubit, the basic unit of quantum information. A single photon was then reflected from the sender's optical resonator and directed through a fiber optic cable to a second resonator, which held the recipient atom. After reflecting from both resonators, the photon was measured, along with the spin state of the first atom. Based on these measurements, a feedback signal was sent to the second atom, causing it to adopt the state of the original qubit. This method was remarkable for its efficiency and simplicity, using only a single photon as a transmission resource to teleport a qubit across 60 meters, a significant step toward practical quantum networks. Could we ever teleport humans? At this point, it's natural to ask, could quantum teleportation ever be used to teleport humans, like in Star Trek? The answer, unfortunately, is a resounding no, at least not anytime soon. Let's break down why. 1. Quantum information versus matter. Quantum teleportation transfers information, not matter. The physical body remains behind, while only data about its state is duplicated elsewhere. 2. Sheer complexity. A human body consists of around 10 to the power of 28 atoms. To teleport a person, every quantum state of every atom would need to be recorded and transmitted without error. This would require more computing power than exists on Earth, by orders of magnitude. 3. Entangled resources. For teleportation to work, you'd need entangled particles already in place at the destination. This means preparing a vast infrastructure ahead of time, possibly entangling trillions of particles and keeping them stable until needed. 4. Decoherence and fragility. Quantum systems are incredibly delicate. They lose their quantum properties, a process called decoherence, when interacting with the environment. Maintaining the quantum state of even a single photon is difficult. Doing so for an entire human body would be nearly impossible. 5. Thermal and energetic demands. To scan and transmit that much data, the process would require temperatures and energies greater than the core of the sun, as well as technology capable of surpassing our current computing capabilities by a quadrillion times. In short, the physics of teleporting people remains squarely in the realm of science fiction. And even if the theoretical and technical hurdles were somehow overcome, a deeper philosophical question would remain. Would the person who reappeared at the destination still be the same person, or just a copy? The future of quantum teleportation. While human teleportation may be far-fetched, the practical applications of quantum teleportation are already taking shape. They include quantum communication networks offering unbreakable encryption, quantum computing systems where information can be transmitted between different processors, secure satellite communication even across continents. These technologies could revolutionize fields ranging from national security to financial systems to scientific research. Final thoughts. Quantum teleportation is not just a scientific curiosity. It is a window into the bizarre yet beautiful reality of the quantum world. It shows us that the universe behaves in ways that often defy intuition, yet can be harnessed for real-world applications with transformative potential. Einstein may have resisted the concept of entanglement, but time has shown that what he once dismissed as spooky action is, in fact, a foundational feature of nature. And as we continue to explore these mysteries, perhaps someday we'll unlock even more secrets hidden within the quantum realm. Until then, teleportation remains a dream, but a dream rooted in real science.